everyone. Hello. So I don't know why others have not joined the session. Do you guys have any idea why others didn't join this session? Guys, okay. So no one is going to say anything. Yeah. Okay. So no worries. So let's start the session. So today we will be studying previous year's assignment 3, right? We will be solving around 10 questions, and my pattern will be as I have told you that first I will, as I have already told you in my previous sessions, it will be like first I will discuss the question, then I will give you some hints so that you can solve the question, and then we'll discuss the answer. Okay, and I would want you to, before me telling you the answer, I would want you to solve the question and tell me the answer. Get to the answer and tell me that. That way it will be really good and you will get the practice and which you can use for solving your own assignment, uh, which is uploaded this year. You can solve those questions, and also these are pretty good questions. So you can also think that you can also get the experience of how to solve gate level questions. So these are pretty good questions. They have good basic concepts are there. So which will help you in solving those questions which come in the gate exam or ESE and other competitive exams. For that also it will help you. So let's start the session. All right. Hmm. Yeah. Also, do let me know if you have any doubt regarding any question. If you get any doubt, you can ask me. Even after the session, when I'm finishing the session, you can ask me your doubts at that time as well. Okay. So let's start the session now. Okay. So is my screen visible to you?
Yes, it is visible now.
Okay. Good. Chalo. So, the first question is, in a long range microwave communication system operating at 9 gigahertz. Okay. Sorry. So, in a long range microwave communication system operating at 9 gigahertz, the transmitting and receiving antennas are identical. They are separated by 10,000 meters. To meet the signal to noise ratio of the receiver, the received power must be at least 10 microwatts. Assuming the two antennas are aligned for maximum reception to each other, including being polarization matched, what should the gains of the transmitting and receiving antennas be when the input power of the transmitting antenna is 10 watts? Okay. So here it's asked that it's given that two antennas are given. One is transmitting and another one is receiving. It is said that the received power must be at least 10 microwatts. Okay. Another thing given is these two antennas are separated by 10,000 meters, and the operating frequency is 9 gigahertz. Now you have to find out the gain of the transmitting and receiving antenna. Also, it is given that the input power of the transmitting antenna is how much? 10 watts. Okay, so the first thing that comes to mind is Friis transmission equation, right? When you see two antennas transmitting and receiving, it has a distance in between. Power is given to you, how much input power and how much input power at the transmitting antenna is given, how much power received should be is given to you, and the operating frequency is given to you. Can we fit all these in a Friis transmission equation and find out the gain, right? uh, One, here it is also given to you that both of the antennas are identical to each other, and it has a polarization matching, right? What does this mean? This means that gain of the transmitter transmitting antenna and gain of the receiving antenna will be same. Why? Because they are identical and their polarization is also matched. Now can you put all of these in the transmission equation and find out the gain? Yes, you can. I'm going to give you 3 minutes. Try to solve this question and then we'll discuss the answer. If you are not comfortable with telling me, you can tell me which option you think is the correct option in the chats here. Where is the chats? Huh. So in the chats here, you tell me which answer you think is the correct one. Okay, and then we'll discuss the solution. Okay, so that you solve this question. You have 4 minutes. Did I give 4 minutes? Yeah, so you have 4 minutes. Go ahead. Yeah, I'm going to show you the transmission equation. The one that I have just highlighted in the box is Friis transmission equation. Okay, this is Friis transmission equation. Use this equation to find out the GT and GR. Okay, answer? Guys, were you able to solve? Was there any doubt you have for this question? Okay. Yeah. So as I told you that this is the first transmission equation that you can use to find out the uh, gain of transmitting and receiving antenna. So here, since transmitting and receiving antennas are identical, the gain will be same, right? Both their gain will be same. Now since frequency is given as f is equals to 9 gigahertz, can we find out the wavelength lambda? Can we find out lambda? Yes, we can, which is equals to E by,
By A. Ma'am.
yeah, uh, what are you saying?
Ma'am, lambda is equal to put the value C by A. Then,
Yeah, yeah. What are you saying?
ma'am, the formula, I'm telling about the formula. Lambda is equal to C by A.
Yes, yes, very good. Yes. So lambda is equals to C by F. So F is given to you, which is equals to 9 gigahertz. We will be able to find out lambda, which is equals to 1 upon 30 meters. You put this value here. R is already given to you. How much R is given? 10,000 meters. You put R is equals to 10,000 meters. Power, received power and transmitted power is given to you. How much input power was given to you? 10 watts, right? Whereas received power is how much? 10 microwatts. Put all the values, we will be able to find out the value of G even in terms of dB. So here, one thing you will notice is that we use dB for gains, because even for antenna, for gain purpose, we use dBi, not even dB. Sometimes for gain we use dBi. What does dBi mean? Dbi dbi means it is the gain, gain is compared with the isotropic antenna. So like, let's say if a antenna has 10 dBi gain, it means that it is 10 dBi 10 dB better than the isotropic antenna. Okay, so we use the unit we use for gain is dBi. Okay. Chalo, let's try to solve. Any doubt you have here? No? Chalo, let's go ahead. Let's try to solve next question. Hmm. So the effective antenna temperature at the input terminal of the antenna is 150 K. Okay, 150 kelvins. The antenna is connected to a receiver through an X band, 8.2 to 12.4 gigahertz. Okay. Rectangular waveguide of 10 meters. Loss of waveguide is 0.313 dB per meters and a temperature of 300 kelvins. Find the effective antenna temperature at the receiver. Okay. So here, uh, one antenna is given to you. Okay. It is connected to a receiver. है ना? That uh, through an X band rectangular waveguide. Okay, so one antenna is given to you which is connected to a receiver through an X band rectangular waveguide of 10 meters. Here it is also given that the waveguide is not ideal, it is a lossy waveguide, and the loss of waveguide is how much? 0.13 dB per meters. Okay, now the effective antenna temperature at input terminal is how much? 150 kelvins. Okay, and the antenna at the receiver end is how much? 300 kelvins. Now you have to find out the effective antenna temperature at the receiver. One second. The antenna is connected to a, okay. So no, so the waveguide, which is of 10 meters long, has a temperature of 300 kelvins. Okay, and you have to find out what? You have to find out the effective antenna temperature at the receiver. Okay, got it? So here one antenna is given. How do I make? Okay, let's say one antenna is let's say this is a Yagi Uda antenna. Okay, so one antenna is connected to a receiver. Okay, some receiver. Let's make it a Yagi Uda antenna only. It is connected to a receiver through a 10-meter rectangular waveguide. Do you know what rectangular waveguide is? A rectangular waveguide is uh, you can say a metallic waveguide, right? It's like a pipe, you know. So have you seen cylindrical pipes in your home? Metallic cylindrical pipes, right? You would have seen that. Wait, I might have something to show you. Something like this, right? So, but hollow. This is a bottle, so it's not a wave guide. So something like this with a hollow here and hollow here. So this is a cylindrical wave guide. It's a metallic cylindrical wave guide. Similarly, you have a rectangular shaped wave guide. Okay. So here it's given that a rectangular shaped wave guide is given to you. So a rectangular shaped waveguide is given to you, and loss of waveguide is 0.13 dB per meters. Okay. Now you have to find out the effective antenna temperature at the receiver. So at the receiver you have to find out the effective temperature. Got it? You got the question? Now I will tell you how to solve this question. So first, so this is loss of waveguide. Loss of waveguide means what? Attenuation constant. Okay, so attenuation constant is in dB per meter. So the first thing that you have to do is convert the attenuation constant into Nepers per meter. First, find out the attenuation constant in Nepers per meter. Then, why am I asking you this? Because the formula for effective antenna temperature at the receiving end and has alpha in it, and this alpha is what? This alpha is attenuation constant. So here I am giving you a formula. Yeah. So I'm giving you a formula for effective antenna temperature at the receiver. Okay, this is the effective. Sorry. So this is the effective temperature antenna temperature value, and for that this is K is Boltzmann constant, B is the bandwidth. Okay, T is temperature of the antenna, TO is the temperature output temperature, and then you have to find out the effective. Sorry, yeah. So you have to find out the effective, which is at the where which is at the receiving end. Okay, so first try to find out alpha in Nepers per meter, and then we'll solve for the effective temperature of the antenna at receiver end. Okay, so uh, okay, so I'm leaving till here and look at it and tell me the answer. Yeah. Okay. Once you find out the attenuation constant, let me know, and then we'll go for effective temperature. Okay. So I'm giving you 3 minutes. Find out the attenuation constant in terms of Nepers per meter. First, do the conversion, and then we'll solve it for effective temperature. Got it? So 3 minutes I'm giving you. Done. Were you able to find out the value of alpha in terms of nippers per meter? So alpha is given as 20 log base 10 E alpha nippers per meter. Okay. So log base 10 E value is a constant which is 0.434 alpha nippers per meter. So here alpha in terms of nippers per meter, alpha dB per meters. So we already know alpha in terms of dB per meters. How much it is? 0.13 dB per meters, right? So so from here we will be able to find out the value of alpha in terms of nipper per meters, which will be equals to 0.149, or you can directly take it as 0.15, right? So 0.14966 nipper per meter. Now you have to find out the effective antenna temperature at receiver end. So this is the formula for you. Okay. Here K is in terms of Boltzmann constant. TA is already given to you. How much is TA given to you? 100 and 150 K. T for T free space. So here we have all you have already seen that the both the antennas are not in the free space, right? They are connected with a rectangular waveguide of 10 meters. So it is not in a free space, it is in a rectangular waveguide of 10 meters with loss. So here you have to put that value. So that temperature is how much? 300 kelvins. So that B is B is again bandwidth. You don't need to find out bandwidth because T effective can directly be written as this divided by KB. So K and B is will already get cancelled, and you will get T effective is equals to TA plus T naught into e to the power minus 2 alpha L. The value of L is how much? 10 meters, right? Here the value of the rectangular waveguide was how much? 10 meters. So here the value of L will be 10 meters. You know TA, you know TO, you know the value of alpha in terms of nippers per meter. You know the value of L. Will you be able to find out T effective? Find out the value of T effective. Tell me in the chats. Okay, I'm giving you 2 minutes. Everything will be cancelled out, and you only have to find out TA plus T naught into e to the power minus 2 alpha by L. Use your calculator and tell me the value of T effective in 2 minutes. Anyone got no replies over here? Okay, fine. You guys are not sitting with your calculators?
लाल फाइल बन
Yes.
Ma'am, it will be 333.36.
333, yes. 333.58 is the correct answer. But yes, you are correct. So option A is the correct answer. Right? Yes, very
Yes,
good.
ma'am.
Very good. Okay. So let's solve next question. For a loop antenna placed at the origin, any doubt anyone? Anyone has any doubt in the previous question? Question number 2? No? Okay. So let's go to question number 3. For a loop antenna, one second. No. Okay. Very good. Yeah. So let's go to question number 3. For a loop antenna placed at the origin with its axis along z axis, the radiated electric far field at radial distance r will be. So a loop antenna is given, right? And it is in z axis. X. This is in z axis, x, y. Okay. And if you take it in terms of phi and theta, then it will be to give you idea of phi and theta in spherical coordinate, right? So this will be xy. So this will be phi and this will be theta. Okay, this getting. So so if this is the loop antenna that we have, then this will be theta and this angle will be phi. So you have to tell that what will be the electric radiated, not radiated, electric field in a far field distance, right? Radially outwards. The electric field will be um, function of theta, or it will be function of phi, or if it will be the function of both, or if it will be the function of r. So think about it. And this is the antenna, a loop antenna, right? Z axis loop antenna. So you have to find out at far field if it will be uh, proportional to theta, if the it will be function of theta, phi, or r, or the combination of all these things. Okay, got it? Think about it and tell me. What about it? Did you guys think has only five components? Yes, yes, very good. Yes, yeah. So, tell me why only phi component will be there and why not theta component? So this is the loop, right? Right? So the theta, if we take 0 and 180 degree, right? Theta will be same, but it will have different phi, right? So think why will the a loop antenna will have only phi component but not theta component? Can anyone tell me why it will be like that? Very good, Professor Dr. J. Rangarajan. That's a yes. So, but why will it be only five component? Okay, so this,
because
yeah, yeah.
because field component is perpendicular to the radius. Field components are perpendicular, and in the direction we have, I think we have only pi component.
Yes, yes, very good. Because theta component won't be coming, right? Because theta, if we say 0 degree theta and 180 degree theta, if we take, it won't be differing, right? The field won't differ. It will be a function of only phi. Getting? If we change the r, if we change no, if we keep the r same but change theta and phi, still for all the theta, for all the values, if it is in far field, it will be in function of phi. Why? Because the loop antenna is not changing in phi. The loop antenna's current carrying is in xy plane, right? It is not in z plane. So the electric field will be also a function of only phi and not theta. Okay. So yeah. So very good. So answer will be has only a phi component. Yeah. For a constant R in a far field, the radiated electric field of a loop antenna has only phi variation. So the correct answer is A. It has only a phi component and no theta component. Okay. So let's go to the second question. Question number 4. Question number 4 here says a center fed electric dipole of length L is attached to a balanced lossless transmission line whose characteristic impedance is 50 ohms. Assuming the dipole is resonant at a given length, find the input VSWR when length is equals to lambda by 2. Okay. So here a center fed, right, dipole of length L is attached to a balanced lossless transmission line. So balanced lossless transmission line means what? It will have a input impedance of 50 ohms, right? Assuming the dipole is resonant at a given length, find the input VSWR when length is lambda by 2. So L is equals to how much? Lambda by 2. So here a dipole antenna is given to you, right? It is connected to a lossless transmission line, right? Now you have to find out the input VSWR. That is the question. So input VSWR can we find out how? First you have to find out the reflection coefficient. So the reflection for a and here you have also given that the dipole's length is lambda by 2. What does that mean? It means that the dipole is a half wave dipole. For a half wave dipole, we already know that the input resistance is how much? 73 ohms plus 42.5 73 plus 42.5 j ohms. So here, if the dipole is resonant, it means that it won't have any imaginary component, it will have only real component. If it will have only real component, the input impedance of the antenna will be half wave dipole uh, input impedance, wait, not input impedance. It means that the impedance of the antenna will be only how what? Only resistance. It won't have any reactive component to it. So, and for half wave dipole, we already know that Z of A is equals to RA is equals to how much? 73 ohms. Okay. So now you have to find out reflection coefficient. You already know how to find out reflection coefficient, right? I've already told you in previous class. Use that formula. Once you use that formula, put it in the VSWR's formula, you will be able to find out the value of VSWR. So formula for VSWR is what? 1 plus modulus of reflection coefficient upon 1 minus modulus of reflection coefficient. Whereas the formula for reflection coefficient is what? Z in minus Z0 upon Z in plus Z0. Right? Z in you already know how much Z in is. Input impedance of antenna is how much? 73 ohms. Whereas Z0 is how much? 50 ohms. 50 ohms. Okay. So, sorry. This 50. Okay. So find out the reflection coefficient, put it in this formula, you will be able to find out the value of VSWR. So use use all of that and tell me what will be the correct answer. So use all the formulas. VSWR is equals to 1 plus modulus of reflection coefficient divided by 1 minus reflection coefficient modulus of reflection coefficient. The value of reflection coefficient is this. Put all the values, you will be able to find out VSWR. So I'm going to give you 2 minutes. Solve it and tell me which is the correct option.
Ma'am, option C will be correct.
Okay, very good. What about others? What others think? Okay, uh, I'm giving you 2 minutes, 3 minutes. Solve it and tell me fast if option C is the correct one or something else. You are getting some other option.
Option C.
Okay, very आपको वो क्या मिल रहा है? टी. ओके ओके ओके, वेरी गुड. Still some of you are left. Tell me if you are able to solve it. And okay, one last 1 minute to solve this question. Okay, okay, yes. Uh, Very good. So answer is correct answer is option C. Yes, that is correct answer. Very good, all of you. So Zin input impedance. So for a half wave dipole, Rin, as I already told you, is 73 ohms. You put it here in the formula for reflection coefficient. You will be able to find out the value of reflection coefficient equals to 0.1867. So VSWR will be 1 plus 0.1867 upon 1 minus 0.1867. So correct answer is 1.46. Okay. Any doubt, anyone? No. Everyone already solved this question. Very good, all of you. So I don't think there is any doubt. But if you have, you ask me now. No. Okay. So let's go and solve next question. What will be the radiation resistance of a circular coil of 10 turns with a uniform current distribution at 10 megahertz if the radius of the loop is 5 centimeter? Okay. So you have to find out radiation resistance, okay, of a circular coil of 10 turns with uniform current distribution at 10 megahertz if the radius of loop is 55 centimeter. So a coil is given to you, right? A circular coil, okay? It has 10 turns. It has a current flowing through it, okay? Having a frequency of 10 megahertz. So a alternating current is flowing into it with a frequency of 10 megahertz. And now you have to find out radiation resistance if the radiation of the radius of the loop is how much? 5 centimeters. Got it? So a coil is given having a radius of 5, current flowing through it is 10 megahertz and radiation resistance is asked. So for this question, radiation resistance can be written as radiation resistance can be written as N square RA. Okay. So N is what? Number of turns, and RA is the radiation resistance of a single turn. Got it? It's a simple. It's a simple thing. Uh, if a coil is given with the n number of turns, okay, then the total radiation resistance will be equals to n square r small a, where r small a is what? It is a radiation resistance of a single turn. Okay. Now r is, this is the, this is very important formula. Okay. This is very important formula for all of you. This is radiation resistance for a single turn. So radiation resistance of a single turn is how much? 320 pi to the power 6 r naught upon lambda naught to the power 4. R naught is what? Radius of loop. Lambda naught is what? The current, the wavelength of the current, alternating current. Okay. So R naught here is 5 centimeters and lambda naught is, this is R naught. Okay. R naught, and corresponding to this, can we find out lambda naught? Can we find out lambda naught? Yes. How? Lambda is equals to what? C by F, right? F, you know, F is how much? 10 megahertz. You know the value of C. Will you be able to find out the value of lambda? Right? It's a pretty simple arithmetic sum. You will be able to find out the value of lambda. Put, put these values here. You will be able to find out radiation resistance of a single turn. When you find that out, you will put it here in this. N is how much? 10 turns. So this is N. This is N. N is given to you. Uh, First, you have to find out R small a, radiation resistance of a single turn, which is equals to this R naught, lambda naught. You already know. Put it here and you'll be able to find out Ra. So do this question. I'm giving you 2-3 minutes. Option C. Okay, no, for the previous one. Okay, so I'm giving you 3 minutes for this question and tell me which is the correct option. Okay, do it fast. Anyone got answer? Do it fast. I'm giving you 2 more minutes. Solve it fast.
Ma'am, option D.
Option D. Okay. Okay. What about others? Solve fast. Solve. Was anyone else able to solve it? किसी ने सॉल्व किया क्या? नहीं? Okay. Leave it then. हम solve करते हैं. So as I already told you, R naught is radius of loop, lambda naught is wavelength. So put all these values here. So first you have to find out the value of lambda naught. As I already told you, lambda naught value will be how can you find that out? C by F. Put that, you will be able to find out how much lambda naught is 30 meters. Put it here. R naught is already given to you, but it is in terms of centimeters. So you have to be very mindful of the units. R naught is in centimeters, lambda naught is in terms of meters. So use the appropriate values, okay? And we will be able to find out radiation resistance for a single turn. Now, radiation resistance for 10 turns will be how much? 10 square, that is N square Ra. This will be the value. So, correct answer is option D. Yes, very good. Very good. Someone told the correct answer. Who said the correct answer?
Ma'am, Sushovan.
Okay, so Shobhan. Yes, so very good. Yes, option D is the correct answer. You anyone has any doubt here? Should we go ahead?
No, madam. No,
Okay,
madam.
okay, very good. Chalo. So similar kind of question again. We are getting a similar question, almost similar, same formulas and everything. Here, what you have to do is question here is a n-turn circular loop with uniform current distribution having circumference of lambda by 100 is wound around a ferrite core of permeability 4.5. Find out the number of turns required to get radiation resistance of 1 ohms. Okay. Here a circular loop is given. Okay. It has a uniform current distribution. All right. It has a circumference. Okay. The circumference is how much? Lambda by 100. Okay. And it has a core which is a ferrite core and has a permeability of 4.5. Now you have to find out number of turns. Okay. So that radiation resistance is 1 ohms. So here what is given to you? Radiation resistance is given to you. That means Ra is given to you. What else is given to you? Circumference is given to you. Can from the circumference will you be able to find out the radius of the loop? Right? Can you find if a circumference is given to you? Circumference is given to you lambda by 100. Will you be able to find out a radius? in terms of lambda? Yes. So find out the
2 pi r.
yes.
That is
Huh. So find out r naught. Okay. From this, find out lambda naught. Uh, yes. You don't need to find out lambda naught because r naught is in terms of lambda only. So both of the terms will cancel out each other. Then radiation resistance is given to you, and you have to find out the how much n will be, how much turns it will be. So first thing is, now that it is not in free space, earlier in the question number 5, the coil was kept in a free space, so there was no permeability factor. But here it has a ferrite core, so it has a permeability factor. So here radiation resistance will be how much? Mu square n square Ra. Okay, got it? It is not in a, this coil is not kept in a free space, so it will also have a factor of permeability mu. So Ra is how much? Mu square n square Ra. But the Ra for radiation resistance of a single term is again the same formula. So use the formula here, and Ra is already given to you. R small a, first find out R small a. R small a is not given to you. Find out R small a. Then put it here, put mu R capital A, value of R capital A, you will be able to find out the value of N square. Solve this question, I am giving you 3 minutes. And tell me which is the correct option. Done? Anyone? Done? Okay, if you are not able to solve, yeah, so as I already told you, what you need to do is convert the circumference into r. Circumference is given as lambda by 100. 2 pi r is equals to circumference. You will be able to r is equals to, sorry, 2 pi r is equals to how much? Lambda by 100. R will be how much? Lambda upon 2 pi 100. Okay. Put this value here in terms of r, r naught, and lambda naught is given to you. Lambda lambda will cancel. How much will it will be? 320 pi by 6. This value 320 pi by 6. uh, 320 pi by 6 into how much? 1 upon 1 by 2 by 100 to lambda naught to the power 4. Okay, lambda naught, lambda naught will get cancelled, and all of the other values are constant. You will be able to find out Ra, which will be equals to how much? 3.08 into 10 to the power minus 3 ohms. This is radiation resistance for a single loop. So then we already know that the final radiation resistance is how much? Mu square n square Ra. Mu you know, Ra you know, R capital A you know. Will you be able to find out the value of n? Right? So you have to use calculator. You will be able to find out the value of n, which will be equals to 4. So how many turns in this loop has? In this yeah, this circular loop has how many turns? 4 turns. Correct answer is option C. Okay, any doubt anyone?
No, madam.
Okay, very good. So let's go to the next question. So the next question is, which one of the following sentences is incorrect? Read the question properly. Here it is said, which of the following sentences is incorrect. Okay, so the first option is the directivity of monopole is twice that of dipole. Can someone tell me if it is a correct or incorrect statement? The first statement is directivity of a monopole is twice that of dipole. Is it correct or incorrect? Okay, so this statement might be confusing to you. So okay, all right. Let's see second statement. So the second statement here says the input resistance of the monopole is half that of dipole. What do you think of that? The input resistance of the monopole is half that of dipole. Can you guess what if this statement is correct or not? Think about it. Monopole means one pole, dipole means two poles, right? Here it is asking input resistance of the monopole pole is half that of dipole. Can this statement be correct or not? We know that R in R any kind of resistance can be said as rho L by A. If length is half, will input resistance be half? If length is double, input resistance will be doubled. So here the statement says input resistance of the monopole is half that of dipole. Can this statement be correct? Yes, it's a correct statement because it's a monopole. So monopole will have half of the input resistance compared to dipole. Yes, this is correct statement. Now, if input resistance is half, does that mean the power will be how much power will it be getting? Okay. Can P be written as half I square R? If input resistance is half, hello PM. This is for monopole, P of dipole, right? Wait, no. This is not correct. This is power dissipated. Okay, think like this. So the input resistance of if the input resistance of monopole is half, it means that the, it will have better radiated power, P radiated, right? Since more power will be flowing, more power it will have more power to radiate in the free space. If it will have more power to radiate in the free space, what does that mean? It means that its directivity will be better. So the statement directivity of monopole is twice that of dipole. What do you think? Is it correct or is it wrong? Input resistance is half, which means the power dissipated will be half, which means the radiated power will be double, which means that the dipole, which means that the directivity will be double, right? Tell me, guys, what do you think? So the input resistance is half of a monopole, right? If we compare it with dipole, so the input resistance of dipole will be something, and the input resistance of monopole will be half of it. So then it will have twice the power radiated, right? If it will have twice the power radiated, it means that the directivity will be twice compared to the dipole antenna. Is this statement correct? What I'm saying? Bolo, bolo, bolo. Yes, it's a correct statement. So, so the directivity of monopole will be twice that of dipole. Yes, it's a correct statement because power radiated will be double. So that means the directivity will be double. Okay. Now, next option. The radiation resistance of monopole is equal to that of dipole. Is this statement correct? Is this statement correct or it's wrong? The radiation resistance of monopole is equal to that of dipole. We know that power radiated PR of M is twice, right? If it is twice, then it is equals to half of I square R A. Here R A is what? One second. It's a very dirty thing. RA. Okay, so power radiated is double. So can we say if current, if same current is flowing in the monopole and dipole, the RA will be double? That is radiation resistance of monopole will be double. This statement here that says that the radiation resistance of monopole is equal to that of dipole is wrong, right? Half of that of dipole. Okay, I need to check if it's a half or if it's a double here. Okay, anyway, so option C is the incorrect one. Now, monopole is an unbalanced antenna. So, yes, this is correct on answer. This is correct that monopole is an unbalanced antenna. So, okay, I need to check if this statement is correct. Radiation resistance of monopole is half that of dipole. I will check this out again. I will confirm it if it's a correct statement or not, and then in next class I will tell you if it's correct or not. Okay. Any doubt here? Anyone?
No,
Yeah.
ma'am.
Let's discuss this question again. Maybe I'm missing something, so I will discuss this question again next time. Okay. Question number 8. A half wave dipole is radiating into free space. The coordinate system is defined so that the origin is at the center of the dipole and the z-axis is aligned with the dipole. Okay, the input power to the dipole is 100 watts. Assuming an overall efficiency of 50%, find the power density in meter square. Is r is equals to 100 meters, theta is equals to 60 degree, and phi is equals to 0 degree. So again, half wave dipole is given to you. Okay, the space is free space. Okay, coordinates are given to you. This half wave dipole is kept at the origin. Okay, axis as z axis. Now input power to this dipole is 100 watts and the efficiency is given as 50%. Find the power density. Power density you have to find out for r is equals to 100 meters, theta is equals to 60 degree, and phi is equals to 0 degree. So, so the formula for a half wave dipole, uh, for a average power density is given as this. Average power density, right? Now in this formula, I naught is unknown. Okay, I naught is unknown to you, but that the if we have radiated power, see, power, input power is given to you, efficiency is given to you, so it is only 50% efficient. So the input power is 100 watts and the antenna is so the half wave dipole antenna is only 50% efficient. So we can find out the power radiated, right? And now we can find out the power radiated. If we found out the power radiated, we will be able to we already know the R radiated. Half for half wave dipole, R radiated is how much? Radiation resistance of half wave dipole is 73 ohms. We'll put it here. Here we know P radiated, R radiated. We don't know I naught. We will be able to find out I naught. Okay, something like this. Now we know the coordinates of the. We know the spherical coordinates. We'll put it here. We will be able to find out power density. Got it? What you have to do? So first thing that you have to do is input power is given to you. Find out radiated power. Efficiency is given to you. You will be able to find out P rad, P radiated, PR. Let's say PR. After that, you put PR is equals to half I naught square R radiated. For R radiated half wave dipole, R radiated of half wave dipole is how much? 73 ohms. So R of R is 73 ohms. Put that in this formula. You will be able to find out I naught. Once you find out I naught, here, put it here. You know all the other terms. You know R square, which is equals to 100 meters whole square. You know theta is equals to 60 degree. You know phi is equals to 0 degree. You will be able to find out WAV. These are the two formulas you have to use. You know all the unknowns. You know all the what you have to find out. So solve this question and tell me what will be the correct option. Okay, are you able to see the whole question and options? Guys, are you able to see the question and the options? Yes.
Yes, ma'am.
Okay, very good.
Yes, yes, ma'am.
Very good. So options are given, formula is given to you. You know the unknowns, how to find out the unknowns. Find find the this WAV, which is power density in terms of W per meter square. You will be able to find out which is the correct option. So tell me which is the correct option. Okay. It looks like it's a very heavy term, cos square pi by 2 cos theta upon sine square theta. It looks very tough. It's not tough. It is not very tough. You will be able to find out the values. It's very easy. It just looks heavy in terms of variables, but it is easy question. So I'm giving you 4 minutes. Solve it and tell me the correct option. Did you get the answer? Any answer? Anything? No? Okay, alright. So as I already told you that for half wave dipole, radiation resistance is how much? 73 ohms. So here you put 73 ohms in R radiated. I naught, value of I naught we don't know, but we know the value of P radiated. P radiated is how much? Efficiency into input power. Efficiency is 0.5, right? Overall efficiency is 50%. So if input is 100 watts and efficiency is 50 watts, that makes radiated power is equals to 50 watts, right? So radiated power is 50 watts. We will be able to find out the value of I naught. I naught value will be 100 by 73, which is equals to 1.37. Now for a point equals to R is equals to 100 meters, theta is equals to 60 degree, phi is equals to 0 degree. For this point, the power density will be this value, which is 1. So efficiency, sorry, yeah, this N is 1 second. Okay, yeah. So this here is not efficiency. This is free space impedance, which is equals to 120 pi or 377 ohms. Okay, do not confuse with the efficiency term. Okay, so this is 377 ohms. You put the value here, value of I naught 8 pi square R square here, and this is pretty simple, cos 60 degree and sin 60 degree. And phi, there is no term for phi, and it's already given that phi is equals to 0 degree, and also no term for phi. So you will, if you solve this question, you will be able to find out WRAV, which is equals to 1.746 into 10 to the power minus 5 watts per meter square. So option D is the correct answer. Got it? You have any doubt here? Okay, okay, very good. Chalo, so let's solve for the next question. So first, you from here in this from this assignment, you take out this that the half the radiation resistance of half wave dipole is 73 ohm, whereas the impedance is 73 plus 42.5 ohms. Okay, so Z input for half wave dipole is 73 ohms plus 42.5 J. 73 plus 42.5 J ohms. Okay. So the next question is dependent on this. So a linear half wavelength dipole is operating at frequency of 1 gigahertz. Okay. From here, find out the value of lambda. Determine the capacitance or inductance that must be placed in series of the dipole so that the antenna becomes resonant. So here it is asking a linear half wavelength dipole is given. Okay, operating frequency is given to you. Now it is asking find out the capacitance or inductance that must be placed in series of the dipole so that the antenna becomes resonant. This half wave dipole becomes resonant. So for a resonant antenna, we know that a resonant antenna won't have any reactance term. It will just have a resistance term in it. Okay, so here we know that the input impedance of half wavelength is 73 plus J 42.5. So if we connect minus J 42.5 in series, then it will, the whole term will become real. And if the whole term impedance becomes real, that means the antenna becomes resonant, right? So x is equals to minus 42.5 is equals to minus 42.5. Okay, now it can be, it's a negative term, right? So it can be replaced by a, this reactance can be given by what? By a capacitor. So the term of capacitor will be how much? 42.5 upon 2 pi f, right? X is equals to minus omega c. We know the value of omega, 2 pi f. Put it here, we will be able to find out the value of capacitance required. Got it? So the capacitance required will be in series, connected in series with antenna will be how much? 6.76 nanofarads. Got it? Any doubt here? Okay, tell me. So here it was asked that to make the antenna resonant, a element was placed in series. But what if we wanted a element to be placed in parallel to make the antenna resonant? What would we have used? So to make the antenna resonant, we want the antenna to become, the impedance of the antenna to become real. So for that we use the capacitor, so that this J42.5 cancels out and we get a resonant antenna. So a capacitor in series can do that. But if we want some element in parallel, what element we will use? We will use, guys.
Ma'am, inductive test.
Yes, yes, very good.
Induct.
Yes, we will use inductor in parallel. Okay. Yes,
Yes, ma'am.
yes, very good. Okay, so let's go and try to solve next question. Any doubt anyone here in question number 9? Okay, okay. So let's go and solve question number 10 then. So question number 10 here is a 3 centimeter long dipole carries a phasor current Im is equals to 10 e to the power j 60 amperes. Okay. Assuming that lambda is equals to 5 centimeters, determine E field at 10 centimeter in the far field from the dipole at theta is equals to 45 degree. So a dipole is given to you. Okay. The length of the dipole is given to you. The current of the dipole is given to you. Lambda is given to you. Now it is asking uh, what will be the electric field at a point whose coordinates are what? 10 centimeter comma 45 degree comma 0. Phi is 0, theta is 45 degrees and r is 10 centimeters. Okay, so E field for a dipole is given like this: j and not Im e to the power j beta naught r upon 2 pi r cos beta naught L by 2 cos theta minus cos beta naught L by 2 upon sin theta. Okay, this formula would have been discussed in class by Professor Amibha Bhattacharya. He would have discussed this formula in the class. Okay, so anyways, now uh, beta naught L by 2, so K naught is how much? K naught, which is free space wave number, can be given as alpha plus j beta. Okay, so alpha here is 0. It's not given, attenuation constant is not given in the question, so alpha is 0. So k naught becomes beta, and k naught is equals to j beta, or modulus of k naught becomes modulus of beta. So beta is how much? Beta becomes how much? 2 pi by lambda. This is what is used here. Beta naught L by 2. So the value of beta naught is 2 pi by lambda into L by 2. So we got the value for this term, beta naught L by 2 here, beta naught L by 2 here is used. It is equals to 0.6 pi. So this heavy term, we can reduce this heavy term into, since we already know beta naught L by 2, we will be able to solve sine theta, cos theta, and sine theta is how much? Theta is equals to 45 degrees, right? So cos theta, sine theta, you know the value, cos 45 degree, sine 45 degree. Beta naught L by 2, you know, put it here, you will be able to find out this term. This term will be how much? 0.7703. Now beta naught R is 2 pi lambda by R. So here lambda is 5 centimeters, R is how much? R is 10 centimeters. So lambda by R is how much? 1 by 2. Sorry, R by lambda is how much? 2. 10 by 5, which is 2. So 2 pi by lambda R, which is equals to 4 pi. So beta naught R is how much? 4 pi. Put in this term. Again here eta naught is 377 ohms or 120 pi. So J eta naught Im is given to you in this term. All the other values are given to you. E theta will be how much? 4260 e to the power 11.52. Okay, so without calculator you won't be able to solve. So if bring calculator this time, bring calculator from the next time. So you solve it. Okay, solve the question by yourself. Anyways, so E theta, modulus of E theta will be how much? 4260 volts per meter. So answer will be B, right? Mod of E theta will be how much? 4260 volts per meter. So this is the formula that you have to use. Professor would have told you this. Just you need to know what you have to put in the terms of B naught L by 2 and then B naught R. Once you know that, you will be able to solve this question. Is there any doubt, anyone? Go ahead, ask if you have any doubt.
No doubt, madam.
Okay, okay, very good. Anyone else, any doubt? Okay, so 1 second. So if you don't have any doubt, then I believe that we can end the session, right? I will post this recording on my YouTube channel, so you can watch there if you get any doubt in solving. And I hope that you were able to learn how to solve these kind of questions. Okay? In assignment 3, this year's assignment 3, there will be questions similar to the ones that I have already taught you, and I'm hoping that you won't get any problem there. You will be able to solve those questions. If you still get any doubt, you can ask me in the next live session, or you can ask me on my comment section on the YouTube channel. Okay? Do you have any doubt now for the assignment that we did? Present. Yeah. Okay. Thank you, ma'am. Yeah. Thank you. Thank you. You are welcome. Thank you for attending the session, guys, and all the best for your assignment number 3, right? All the best. Okay, so we'll meet next week then. Okay, bye bye.
Bye, madam. Thank you.